530 million years ago, long before the age of dinosaurs, no living creature, not even a blade of grass, existed on land. Earth was desolate and barren, littered with rock and sand. But deep in a world below the sea, a host of curious creatures flourished in a habitat rich with life. The common ancestors of man and all other vertebrates appeared around this time. So did other mysterious and bizarre life forms that have since vanished from the planet. The Rocky Mountains stand majestically over western Canada. 500 million years ago, this entire mountain range was at the bottom of the sea. Hidden inside these craggy peaks is a geological treasure trove of perfectly preserved Cambrian fossils. Discovered in 1909, this remote part of British Columbia is known as the Burgess Shale. During the brief summer, a group of scientists led by paleontologist Dr. Desmond Collins from Canada's Royal Ontario Museum arrives at the site. The mountain camp will be their home for the next several weeks as the team prepares to search for clues to our past. Buried in the layers of this sedimented rock are the fossilized remains of ancient animals.
Well, the Burgess Shale is, I think, is no doubt the most important fossil locality in the world because it shows more of the possibilities of life which were actually developed on Earth. Most fossils are the remains of skeletons or shells of animals, the hard parts which have been mineralized. In the Burgess Shale, you get those fossils, but you also get the soft tissues along with the hard parts, and also the remains of animals which have no hard parts at all, like worms and jellyfishes. The more we dig, the more we find, and the more we find, the more we realize we don't know. It's a sort of a cumulative thing. It's an exciting place to be because the next rock might expose an entirely new form of life no one has ever seen before. Yeah. I'm interested, of course, in the claw, too.
I don't know.
Oh, no, the tips of spines, I suppose.
Yeah, it's got little spine tips a lot. Yeah.
More than 100 specimens from the Cambrian period have been collected here. the finely layered rock peels away like leaves from an ancient book. Fossils emerge one after another, almost leaping off the pages.
Actually, I think in front. Yeah, 4.
Many of these animals are extraordinarily complex. Some even look like creatures out of science fiction. The sheer volume of animal life preserved in the Burgess Shale makes it one of the world's most enticing spots for fossil hunters. Only a small section has been excavated to date. At one time, these rugged mile-high peaks lay deep below the sea. Half a billion years ago, towering cliffs harboring a city of ancient life rose from the sea floor. Then, one day, a powerful landslide. In an instant, cliff dwellings turned to rubble. Buried under tons of muddy debris, every living creature would perish. But in this airless tomb, their remains would lie in pristine condition, untouched by scavengers or decay. Repeated landslides deposited sediment, eventually forming what is now known as the Burgess Shale. Paleontologists from across the globe visit this site, hoping they will be the next to tap into its rich cache of Cambrian history. An air of anticipation hovers over the mountainside where Dr. Collins and his team explore.
Where's Matt? Matt, come here for a second. Check it out, man. Look at the eyes on the thing.
It's got eyes.
Oh, yeah, big eyes.
Huge eyes. Show them.
Another chapter of our ancient past comes to life.
Wow.
Wow.
Doctor, what is it?
I don't know. That's the,
Right on.
that's completely new. Completely new.
So what are you going to call it?
What's the name for it?
I guess this is a, you found it, didn't you?
Mm-hmm.
I guess that's an Andrewsaurus.
Solving the mysteries of the Cambrian Age has challenged researchers here at Cambridge University. One look at the pristine Burgess Shale fossils in the early 1970s piqued the imagination of Dr. Harry Whittington. He decided to launch a full-scale study of the enigmatic Cambrian creatures. This was one of the fossils that fascinated him. An animal with a long nozzle protruding from the head. At first, it looked like an extension of the mouth, but closer inspection placed the mouth at the tip of the U-shaped digestive tract, way below the head. If the mouth and nozzle weren't even connected, Whittington wondered, what purpose could the nozzle serve? To find out, Whittington re-examined fossils from his own collection along with recently excavated Burgess Shale finds. To his delight, he discovered a new specimen of this strange creature. With a small drill, he slowly chipped away the rock layer covering the fossil. split in two like a pair of scissors, the tip of the nozzle soon emerged. The nozzle, it seems, was used like an elephant's trunk to grasp food and carry it to the mouth. Dr. Whittington noticed another peculiarity. The white spots on the head were thought to be the eyes, but there were more than two. This creature had 5 eyes. The animal Dr. Whittington reconstructed based on fossil analysis amused the scientific community with its cartoon-like features.
I drew a reconstruction of it and I showed it at a meeting of paleontologists, and they all shouted with laughter because it was such an impossible looking animal with no legs to walk on, must have swum by flapping these flaps, and it had this great process in front of it and these eyes sticking up on the head. But I think that's, well, the most careful investigation I can make suggested that that's what it was really like. That's what I was interested in.
Resurrected after more than 500 million years of extinction, this offbeat organism was named Opabinia. One by one, other ancient life forms discovered at the Burgess Shale were reconstructed by Dr. Whittington and his research team. The work could be tedious. At times, it took over 3 years to reassemble just one fossil. But gradually, the story of Cambrian life was unfolding. Because of its bizarre appearance, this creature was named Hallucigenia. With spikes protruding from its narrow body, it's hard to tell which end is up. Nectocaris looks as if it were fused from 2 different animals. It has a head like a shrimp and body like a fish. Dinomyscus resembles a flower, but it's really an animal, not a plant. On the inside of the petal-like parts, the mouth and anus lie side by side. Odontogryphus has small tooth-like protrusions around its mouth. Its name literally means mystery with teeth. At one time, Cambrian fauna were thought to be simple creatures with little diversity. But Dr. Whittington and his team proved otherwise. These life forms already exhibited complex structure and a rich variety of shapes and design. Among them were creatures so unique that at first they defied any biological classification. 10,000 new species developed during this era. The Cambrian seas were exploding with life, though why this evolutionary burst occurred is still unclear. Over the past century, scientists have been stumped by one particular Cambrian mystery: the appearance of a predator that terrorized the ancient seas. Even hard-shelled trilobites like this one were not immune from attack. The W-shaped scar was no doubt the mark of a large animal with extremely sharp teeth. But no fossils of such a monster had been recorded. There were many pieces to the puzzle. A fossil first identified as an ancient jellyfish. Dr. Simon Conway Morris was one of the Cambridge researchers who made the connection.
But it's a very peculiar sort of jellyfish because it looks more like a pineapple ring, in as much as there is a hole right the way through the center of the specimen. And there's no jellyfish looking like that today. And we imagined, or at least I did, that somehow the jellyfish was able to place itself over the prey and then the prongs in the middle would squeeze together.
Around the same time, another colleague, Dr. Derek Briggs of the University of Bristol, was studying some peculiar shrimp-like fossils. Named Anomalocaris, or odd shrimp, the fossils were classified as the tail of a shrimp-like creature. Curiously, close to 100 of these fossils had been found, but not one with its head intact. Dr. Briggs began to suspect there was something wrong with the shrimp tail theory. If it were in fact a tail, why were there no traces of a digestive tract? Perhaps, he speculated, these were legs of some other animal. A giant centipede-like creature might have been able to attack a 6 to 12-inch trilobite. But aside from these legs, no fossil revealing the body or mouth of such an animal could be reconstructed. Dr. Briggs' research came to a standstill. That is, until 1982, when Dr. Whittington happened upon something interesting while rummaging through his fossil collection. The imprint on this fossil looked like the body of some animal. Just what kind of animal was harder to tell. Curiosity mounting, Whittington carefully chipped away at the surface and was stunned by what emerged. The fossil now revealed a shrimp-like tail, and next to it, a semicircular impression. It was part of the fossil once pronounced a jellyfish. At the bottom left, the imprint looked like the tip of an early crustacean. These three specimens, identified as different organisms, might all be parts of one animal, Dr. Whittington ventured. The jellyfish-like fossil might be the mouth, and the shrimp-like tail another appendage. At last, in 1991, a new Anomalocaris fossil discovered at the Burgess Shale confirmed Dr. Whittington's theory. This fossil clearly showed two powerful arms growing out of the head, as Whittington imagined, and eyes at the base of these spiny growths. On another fossil, a tail-like segment clearly emerged. After more than a century of speculation, a portrait of the fearsome Anomalocaris came to light. Growing up to 2 feet long and flanked by 14 pairs of overlapping flaps, Anomalocaris was the largest creature of the Cambrian period. The most baffling feature to Dr. Whittington was the round mouth with its circular array of teeth. What did it eat, and how could it capture its prey? Working with Dr. Whittington and his British colleagues to test their theories, the Japanese Broadcasting Corporation, NHK, constructed a model of Anomalocaris for this television series.
Is it possible to turn it upside down, and is it very delicate? Oh, I see. Here's the other part.
Oh, okay. So it can be.
Oh, this is the way it's...
How the mouth functioned was of keen interest to all three men.
But it's...
With its jagged plates that opened and closed like the iris of a camera lens, Whittington, Briggs, and Conway Morris believed this ancient hunter trapped and guillotined its prey.
And we were thinking of this sort of...
Would this Anomalocaris replica leave the signature W-shaped scar on the trilobite models?
Oh, bite, yeah.
Oh, yeah, it does. Yes, well, it still is the same shape of thing.
Mm-hmm. What it's done is split away here, but the shape of the bite there is not very different from some of those.
And it has this... I mean, it's a W shape.
Potential shape, that's right.
Yeah.
So it's certainly plausible.
Yes.
What happens if you try it now? Like that. You can see now how you'd get a more substantial breaking away, rather like some of these here.
The Anomalocaris replica took a perfect W-shaped bite of the trilobite. Another piece of the Cambrian puzzle falls into place. Undulating its numerous flaps in wave-like motion, Dr. Whittington says this animal was highly maneuverable, traveling forwards and backwards with ease. Trolling the Cambrian seas, it preyed on mid-ocean and bottom-dwelling creatures with deadly accuracy. The evolution of stealthy hunters like Anomalocaris may have been a contributing factor to the so-called Cambrian explosion. The eat or be eaten struggle for survival prompted structural diversity. The five eyes on top of Opabinia's head were probably more useful for evading predators than searching for food. Once its enemies were spotted, Opabinia would dash to safety. Hallucigenia and Wiwaxia sprouted sharp defensive spines. Escaping effectively was a necessary art, and many defensive swimming techniques were tested. Some animals developed fins at the base of their legs, allowing them to swim and walk. Fleeing predators, some moved sideways through the ocean. Others undulated up and down. Tiny animals that fed on smaller organisms tried to outwit larger predators. Sometimes burying themselves in the muddy ocean floor. To protect themselves and their offspring, the creatures of the Cambrian period tried on every possible anatomical costume. Yet few of these designs, including the formidable Anomalocaris, would survive. Of all the sea life stalked by Anomalocaris, Pikaia, a tiny worm-like creature, somehow escaped extinction. This bit of an animal had no protective shell or defensive spines. But in the Cambrian period, one part of its design was wholly unique. As Conway Morris discovered, Pikaia has a structure remarkably similar to a modern-day animal called Amphioxus. Both are equipped with a long, stiff rod running the length of the body, the notochord. The notochord, which supported Picaia's muscle structure, is the design common to all vertebrates. This modest creature may be our earliest recognizable ancestor.
Pikaia, I believe, evolved into something like a fish, and from the fish, of course, we have the amphibians, represented today by the frogs and the salamanders, for instance, which invaded land in the Devonian. And then after that, we have the reptiles and the mammals. So perhaps if Pikaia had not survived, if it had gone extinct at some time, then of course ultimately there would have been no mammals and of course no humans.
Though much about our lineage remains a mystery, the origins of the human backbone are linked to Pikaia and its notochord. Few developments would lead to greater diversity. The reign of Anomalocaris was not short-lived. It flourished for nearly 20 million years, 100 times longer than the entire history of Homo sapiens. But in the evolutionary lottery, it was the lowly Pikaia that survived, bearing offspring that would eventually populate the seas, the land, and the skies. California's Death Valley, one of the most arid regions in the world. 400 million years ago, an enormous river filled this valley, linking it to the distant sea. It was here that the fossils of the first fish to brave the freshwater habitat were found. It had taken them 60 million years to gain access to these estuaries. The man who discovered the fossil was Dr. David Elliott of Northern Arizona University, a specialist on ancient fish.
The rocks have been slid.
Tons of earth and sand formed sediments at this site, deposited by the river that ran through Death Valley eons ago. And it is here that Dr. Elliott has been focusing his excavation and research work on ancient freshwater pioneers.
Can't really tell what that is. This is a pteraspid, this is a lingulid. And lingulids are rather interesting because they're characteristic of estuarine environments, that is, environments in which freshwater and marine waters are mingling. These are areas of very high nutrients where you may have large numbers of organisms coming to feed, and we have many pteraspids here. There are also areas that many marine organisms can't get into. They're not able to survive in brackish conditions, and so it may be that pteraspids were protected from some of their possible predators by living in these environments.
Freshwater habitats have almost no salt content. A change in salinity can spell instant death for unacclimated marine life. This paramecium thrives in the salty medium of seawater. Breathing saline fluid, it regulates its mineral levels and ejects wastes. Salt-free water is added, changing the balance. In this unfamiliar, hostile freshwater environment, the paramecium takes in water without voiding it, destroying the cell. The now bloated paramecium ruptures and dies. Pteraspis is about 8 inches long, its head covered with tough bony armor and its body with primitive scales. Unlike paramecium, Pteraspis managed to adjust to this new freshwater habitat with a little creative bioengineering. The pteraspid's protective shell prevented water from penetrating the body through its outer layers, but the gills it used to breathe were a weak spot. To balance its system, Pteraspis developed a kidney powerful enough to pump extraneous water from its bloodstream. Transforming its physiology was a major evolutionary breakthrough for the first freshwater fish, but it was only a first step. "400 million years ago, life on the river was unfolding. But the freshwater habitat posed new challenges, rapid currents and waterfalls to negotiate. It took millions of years for marine life to adapt to these new ecosystems. To survive here, Earth's first fish would experiment with many anatomical designs. Miguasha Park lies on northeastern Canada's Gaspé Peninsula. 400 million years ago, this was a tropical region situated directly under the equator. Etched in this meandering stretch of cliffs is the 20-million-year history of fish evolution. Fossils of freshwater pioneers, fish with fins to resist river current, carnivorous fish with jaws and teeth,
evenly distributed. There's some layers with more osmosis.
and a peculiar fish entirely different from any of the others. This fish had a backbone. Until now, there were fish with tough exoskeletons, but none with hard bone inside the body. Cheirolepis, the earliest creature with a spine, appeared 390 million years ago. The most common fish today, the bony fishes, are its direct descendants. Like modern fish, Cheirolepis was equipped with one pair each of pelvic and pectoral fins. It was sleek, with jaws and sharp teeth for catching prey. Acquiring a spine, Cheirolepis developed strong muscles to swim with speed and power. But there were other agile swimmers in the river that had managed to do without one. Why then did the backbone develop? While the sea was rich in minerals essential to life, the river was in short supply. This is heart tissue. Working in unison, these cells allow the heart to pump blood throughout the body. To function properly, the heart needs calcium. Calcium concentration in a river is in perpetual flux. When levels are high, calcium is stored as bone. When they're low, the bone reservoir supplies the necessary mineral, regardless of external conditions. Meanwhile, the seemingly solid bone is constantly being replenished. At the top of the screen, hard bone is visible. Moving below are cells that dissolve it. Once the bone is dissolved, calcium circulates through the bloodstream to every part of the body. The fate of ancient fish rests on a simple backbone. Those without eventually perished from calcium deficiency or returned to their native sea. For many years, Chirolepis reigned as the king of freshwater fish. His anatomy gained him independence from the marine world. Today, the descendants of Chirolepis thrive in both fresh and saltwater habitats. The river was a proving ground for the earliest fish and their offspring. And in this new habitat, they gradually adapted the body system's key to survival on land. Another fish with a backbone appeared on the river at about the time of Chirolepis. It was called Eusthenopteron, a bottom dweller. Eusthenopteron was not an efficient swimmer like many fish, but it had secured an evolutionary niche with powerful bony fins to push its way through the river's undergrowth. This fish was a stealthy hunter poised for action. Eusthenopteron's habitat shaped its unusual bone structure, which would one day lead to the evolution of terrestrial animals. South America's Amazon breeds acres of jungle swampland, mimicking conditions in the age of Eusthenopteron. And with the swamps, a host of unusual life forms. Among them, the lungfish, a mud-dwelling creature. This fish has gills, but it also has lungs for breathing air. In such murky water, oxygen content is often very low. The lungfish probably developed lungs to breathe oxygen from the air when the supply in the water was depleted. Just as his ancestor Eusthenopteron had done eons before. Poking its head above the surface for a life-sustaining breath, Eusthenopteron surely caught a glimpse of the world above the waterline. Now that fish had evolved kidneys, bone, and lungs, land was almost within reach. The first four-legged creature appeared 10 million years after Eusthenopteron. Its remains discovered in a forest in Scotland. At the time, this region resembled today's Amazonian swampland.
Is that bone or is it a pebble?
Dr. Per Erik Ahlberg of the British Natural History Museum has been studying the earliest tetrapods. He's trying to find out how and why limbs evolved from fins. Only 10 fossil pieces have been discovered to date. But even from these few specimens, an image of this new creature is emerging. Almost 5 feet long, it looks like today's giant salamander.
I suspect that the reason why limbs evolved was because these animals were living in very shallow water, and limbs can be rather better than fins for moving in those sort of conditions, even if you're not really moving onto land. These earliest tetrapods with limbs rather than paired fins still have gills, tail fins, and other features which suggest that they were very much aquatic animals. So I don't really believe that they were using the legs for walking purposefully over land. They might have made short excursions over land, but more probably they were using those limbs in shallow water.
Today's giant salamander still spends most of its time in the water. Negotiating the shallows is a matter of walking, not swimming. Even in swift currents, the salamander plants its feet on the river bottom and moves around with ease, aided by its natural buoyancy. To move as fluidly on land, the salamander would require a far sturdier skeletal structure. "360 million years ago, the once barren earth lay under a canopy of green. Giant forests thrived, and small insects now burrowed in the shady wetlands and soil. This landscape was ready to support new life. But to take their first step on land, our ancestors had one more obstacle to overcome: gravity. This is Ichthyostega, an animal that surfaced 10 million years after the earliest four-legged creatures. Judging from the size of his skull, Ichthyostega measured nearly 4 feet long, its backbone and hind legs clearly defined. But this animal also had thick finger bones and a sturdy skeletal structure. Scientists conclude this was the first creature to walk on land. For the first time, an animal with a supporting skeleton around its backbone. The rib cage protected vital organs like the heart and lungs. On land, without the buoyancy of water to cushion them, these organs would be crushed by the animal's weight. By developing ribs, Ichthyostega emerged in a body that could withstand Earth's gravity and move about freely over land. At long last, the time had come to look beyond the water's edge. A 100 million years had passed since the earliest fish ventured from the ocean into fresh water. A habitat that helped shape the complex body systems necessary for life on land. Bolstered by millions of years of evolutionary advancement, Ichthyostega took its first steps while an ocean of life swam in its bones. From sea to river and from river to land, life had taken leaps of astonishing complexity. There is no way to know what called Ichthyostega from the relative comfort of the river toward the challenges that awaited on land. But in taking its first steps, Ichthyostega blazed a new trail, a path we too would forge on our own evolutionary journey from the nurturing seas into the great unknown.